In this movie, we're going to discuss how a neuron establishes a resting membrane potential. As you'll see, the resting membrane potential is similar to the equilibrium potential that we discussed in the last movie, but there are a few twists. So let's start off with a cell. And first, of course, we have a membrane that separates the inside of the cell on the bottom from the extracellular fluids that bathe the cell on the top. And of course, the extracellular fluids have a high concentration of sodium, and the inside of the cell has a low concentration of sodium. In contrast, the inside of the cell has a high concentration of potassium, and the outside of the cell has a low concentration of potassium. Chloride is high on the outside and low on the inside. Ions cannot pass through the membrane. It's impermeable to ions, and that's a very, very important point. So now we have to make the membrane semi-permeable. And in order to do that, I'm going to insert purple potassium channels. Now I call them purple potassium channels only because purple rhymes with potassium and it makes it a bit easier to remember. So we have potassium channels inserted into the membrane, and these channels are permeable only to potassium and will pass nothing else. So, sodium can't pass, chloride can't pass, and the only thing that passes through the channel is potassium. Because the concentration of potassium is higher inside the cell than outside the cell, potassium is driven out by its concentration force, and it leaves behind negative charges that build up as the efflux of potassium continues. A small negative charge, you lose more positive. The negative charge builds up inside the cell, and it continues to build up as you lose more and more potassiums. The cell finally reaches the potassium equilibrium potential, where the inside is so negative that for each potassium driven out of the cell by its concentration force, an equal number are attracted back into the cell by the negativity in the cell. That is the electrical force. One in, one out, one in, one out, one in, one out. One driven out by the concentration force and an equal number attracted in by the electrical force. This is exactly the same thing that we went through previously in the previous movie. And this happens only if the cell is purely permeable to potassium and to nothing else. Nothing else can happen. The cell is neither gaining positive charges nor losing positive charges at this point. That's why it's at equilibrium. So up to this point, we have an ideal membrane. And what I mean by ideal, it only has potassium channels that are only permeable to potassium. And as a consequence, the cell will reach the potassium equilibrium potential because nothing else can come in or go out, only potassium. But membranes of cells are not perfect. The situation is not ideal. There is also a very small but significant permeability to sodium because there are a few open sodium channels in membranes. And I'm going to illustrate that by inserting this green sodium channel into the membrane. So now the membrane has a small permeability to sodium because there are only a few channels and a large permeability to potassium. But because it has a small permeability to sodium, sodium is going to be driven into the cell by both its concentration force, because it's more concentrated on the outside than the inside, and by the electrical force attracting it into the cell. The electrical force, of course, is the negativity in the cell, which attracts the positive sodium ions. Watch. So whenever you get an influx of positive charge, it reduces the negativity inside the cell just slightly. But because of the reduced negativity inside the cell, there's now not enough negative charges to hold in all the potassium inside the cell. And some potassium ions are driven to the outside of the cell by the potassium concentration force. There it goes. There goes another one. And that reestablishes the potassium equilibrium potential. At least it tries to. That is, you've lost positive charge and now you've made the inside of the cell a little bit more negative. The problem is the ion exchange will go on like this and will reach a steady state at some membrane potential. Look, influx of sodium reduces the inside negativity, which allows the efflux of potassium that will reestablish that. Influx of sodium reduces negativity, allowing the concentration force to drive some potassium out. And this is going to continue in, out, until some membrane potential or some steady state is established. And of course, this goes on simultaneously, the influx of sodium and simultaneously the efflux of potassium. What happens at the steady state is that the membrane potential isn't at the potassium equilibrium potential. The potassium equilibrium potential is minus 75 millivolts. The small amount of sodium influx subtracts from that potassium equilibrium potential, and the steady state membrane potential is slightly less than the potassium equilibrium potential due to the small influx of sodium ions. It is actually about minus 70 millivolts inside negative for reasons I'll show you in the next movie. This potential is most commonly called the cell's resting membrane potential. And in the next movie, I'm going to show you how we can actually calculate the resting membrane potential and give it a specific number in millivolts.